And I think that's a good introduction. Anyway, Ken Czepelka.
Hey everyone, thanks for coming. I made up this list of things I wanted to cover last night, and I timed myself, and I went way over. It's like, oh boy, it's not so easy to explain how to use a scope in a very short period of time. So what I'm going to do really is focus on just really the most basic things that a scope can do, how it relates to electronics, signals, and things like that. And a number of you have your own scopes, I see. And what I want to focus on is the commonality between the controls that are common to all oscilloscopes, and that includes digital oscilloscopes and analog oscilloscopes. Does everyone have one of these? Anyone missing one? Okay. What we have here is a really fine analog scope, the Tech 2467, which is about 30 years old and is still one of the finest oscilloscopes in the industry. I'm hoping to get one from eBay soon. The sections of the scope over on the left is the display. And first, let me just ask a few simple questions. Does anyone know what everyone that knows what it means when I say frequency? How many people understand the word frequency? Okay, pretty much everyone.
Right, yeah.
Okay, I'll go into that a little bit. Voltage. Okay, all right. Okay, good. Well, time. Everyone knows time?
Oh, no,
We've
wait
all
a
seen
minute.
the time
That's debatable.
Okay. In a nutshell, an oscilloscope, digital or analog, doesn't matter. An oscilloscope displays a graph of voltage over time. Okay? That's it. That's what an oscilloscope is. Okay? So, there is the x-axis, which is your time. Okay? It always moves from the left to the right. As it's moving from the left to the right, it's ticking off seconds or milliseconds or microseconds. It'll sweep across the screen as fast as you like or as slow as you like. The y-axis on the graph displays the voltage. Okay? If there were no sweep, and there's a dot in the center, that dot would move up. If you applied a positive voltage, like let's say a 9-volt battery, to the probe, it would go below the line if you reverse the battery, put on minus 9 volts. If you talked into a microphone and looked at the microphone, that dot would just wiggle up and down. In other words, it's just capturing the voltage as it's coming into the scope. Okay. So between the two, between time going this way and voltage going this way, the scope will draw out a graph of voltage changing over time. And that's it. Okay, so that's that's what scopes do. That's what they're all about. That's why they exist. Now, the thing is that electronics, which is, well, you must have some interest in electronics because this is the Arduino group. So everything that's electronic is circuitry that passes electrons, and you normally can't see that with your eyes. But if you probe a circuit, you can observe the voltage going on in that circuit over time, and you can see what's happening in that circuit. So by probing various parts of a circuit, you can tell what's going on. So it's very much like a doctor using a stethoscope. You can tell what's going on in a circuit just by probing around in a circuit. Everything that goes on in a circuit is voltage. It's current. You can't see current. Current manifests into voltage when it goes through a resistance. That's just basic electronics. So you can probe something and you can see voltages at any point in a circuit. In the Arduino chip, that's a digital type of electronic circuit, which means that the voltage will usually go up, go down, and go up, and go down. And you can probe it, and on the scope, it would look just like that. It would register 3 volts, 0 volts, 3 volts, 0 volts, 3 volts, 0 volts, 3 volts, 0 volts, like that. So you can see what, like a flashing LED, for example, on an Arduino circuit, that will be, one side of the LED will be tied to some voltage, like 3 volts. The other side will be connected to the processor, and if you were to probe that, if the LED is flashing, and the LED is on, if you were to probe it, you would see that the other end of that LED was probably at ground, 0 volts. And when the LED shut off, you would probably see that voltage go up to 3.3 volts, and there wouldn't be any voltage across the LED at all. So, so now, how to use, oh, that's good, Dave. That's great.
See if I can get that a little bigger.
Okay, so the sections of the scope. So this is, of course, the display, and that's what draws your XY graph. Right below it are the display controls. All oscilloscopes have display controls. This is like the controls on an old TV set where you have your intensity, how bright your display is going to be, focus. Sometimes it'll be out of focus, it'll be a blur. You want to shrink it down to a nice sharp dot. Scale illumination, which is there's a grid etched into the glass. Sometimes it's hard to see. You can light up the grid, and so you can see the grid better relative to the display. Okay, so that's just all the display. That's just to make your life easier when you're looking at it. The horizontal channel, I'll jump right to that. The horizontal channel, all scopes have a horizontal channel. The horizontal section is an oscillator, and it's responsible for making the beam sweep along the x-axis. Okay, that's all it does. So it's internal to the scope. It doesn't have any inputs or anything like that. It's got knobs to set the settings, but it just does its thing. It just sweeps that beam across the display from left to right, left to right. The knob in the center, this is the horizontal sweep right here. The knob in the center is your sweep speed, okay? And I will show you, it's probably easier to see the sweep speed right here. On the scope, I can set this to 1. I'm going to ground the input channel. Just remove the probe here and put this here. So this is just the horizontal sweep doing its thing, okay? So that setting right now is set for, I think, about 1 second per division. Okay, there's 10 divisions on the screen, so it takes about 10 seconds to sweep across the screen. I think I'll have it set a little faster than that. We'll set that. That's one sweep per 1 second per division. Okay. All right. So the horizontal section, and this is on every single scope. The horizontal section has the knob that allows you to set how fast you sweep that beam across the display. And all scopes, also, this is just something maybe Tektronix. Tektronix was like the originator of scopes. They had scopes, in World War II and everything like that. They had big tube scopes and everything. That's how they built the ENIAC computer. And all scopes are calibrated in 5-2-1 increments. So it's 5-2-1, 5-2-1, and that would be 5 seconds, 2 seconds, 1 second per division. And then a half a second, or 500 milliseconds, 200 milliseconds, 100 milliseconds, then 50 milliseconds, 20 milliseconds, 10 milliseconds, all the way up to, most scopes can go up to about typically 20 nanoseconds, 20 billionths of a second per division. Okay. Now, that's really fast, okay? You can look at radio signals with a speed like that. And that literally, on an analog scope, literally means that beam is sweeping across the screen in 20 billionths of a second if you have the horizontal sweep set that way. Okay, so enough about the horizontal channel. Now we come to the vertical channel. Okay, the vertical channel on this here on all scopes Most scopes have 2 channels. Some toy scopes have 1 channel. You don't even want to deal with toy scopes. Most scopes have 2 channels. Many now have 4 channels. Okay, 2 channels is enough. 2 channels is fine. Each channel has a BNC type input connector, industry standard type input connector. Now, unlike the horizontal channel, the vertical channel actually does take input from the outside world. Okay, and that input would be through a scope probe. Okay, and this is a scope probe right here, and this is simply what it sounds like. All scopes have these. These are scope probes, and this is the BNC, plugs into the scope, and on the other end is the tip, which is very pointy. Don't poke it in your eye. You might want to, measure the voltage in your eye. You can do that, but there's safe ways to do it. You don't want to just poke it in there. And then the ground clip. Now, voltage always refers to voltage relative to something else, usually ground. Okay. So if you have a 9-volt battery, there's no such thing as absolute 9 volts. Einstein made it very clear everything's relative, and that goes for voltage. A 9-volt battery means that the positive terminal is 9 volts relative to the negative terminal. It's 9 volts above the negative terminal. If you put the ground clip on the negative terminal of a battery and put the probe tip on the positive end of the battery, your vertical will move up above the horizontal line by 9 volts. Okay, so that's voltage, and that's the scope probe. And this probe I have hooked up to this signal generator. Now, a signal generator is nothing more than a device that generates. Did I do something with that? That generates a varying voltage over time. So it's, as you can imagine here, a varying voltage over time. Well, hey, that's like the perfect piece of gear to use with an oscilloscope, since an oscilloscope displays voltage over time. Okay, now, one thing that confused me when I was first learning about scopes, when I was very, very young, is I got that, okay, so we got 0 volts here, because there's nothing plugged into the vertical channel, okay? But I can move this knob, so doesn't that kind of mean like that I'm adding a voltage to it or something like that? That always confused me. I never really got that. It does not. What this does is when there's nothing plugged into the channel, or if the channel is set to ground, which grounds the probe, wherever you put this is just your reference. That would be like the negative side of a battery if you want to measure the voltage on a battery. And you can set that wherever you like to be convenient. Okay, I'm not sure that all of you are seeing this here, so I will just anyway, I'm just moving the vertical trace up and down. So for now, I'm going to put it in the center because I'm going to set the signal generator up so that it puts out first a positive voltage and then a negative voltage over time. Okay, so I'll plug this in. And it does have an offset on it. I will just set this to 0. Pop that in. I'll set it to 0. And okay, so I'll give you the most fundamental waveform here. This is a sine wave. This is what nature is made of. This is the purest signal in the universe, and it has no harmonics. And as you can see, this sine wave is tracing out a voltage, first a positive voltage, then negative voltage, then positive, and so on. Okay, there's different kinds of waveforms you can generate. We've got a square wave, which is kind of like if you were to just tap a battery terminal, you would see it would go up and down, up and down. That's called a square wave. Okay, and then you've got a pulse, which is just a modified square wave. And again, sorry, I'm not getting everyone in here. So we've got a modified square wave here. A pulse is just a square wave where you've got one side of the cycle shorter or longer than the other. It's a negative pulse. Okay, there's a triangle wave and a sawtooth wave. Sawtooth because it looks like a saw, that sort of thing. Okay, so that's the second section, the vertical display. Now, on the vertical channel, again, you've got voltages vary. You can look at a signal, like a signal out of a microphone, which I'll show you in a second here, which has a very, very low voltage, thousandths of a volt. So if you want to be able to draw a decent sized graph of it, you want to do what's called increase the sensitivity of the input. So you would turn it to the left to get down from 5 volts per division. Again, it's 521, 521. And it goes from, on most scopes, from 5 millivolts, millivolt being a thousandth of a volt, okay, 5 millivolts all the way up to 5 volts per division. Now with a probe, you can flip a switch that's got a 10 times attenuation on it to expand the range to 50 volts per division. So that means you can get 400 volts peak to peak on most typical scopes, and of course there's ways to expand that with additional attenuators, but you can probe your AC outlet and see your AC waveform easy enough just by going up on the ranges there. Okay, now I'm going to move on to, so does everyone have the horizontal, everyone understands the horizontal channel?
Okay, so if you over voltage it, does it just go off the screen, or we actually damage the unit?
You won't damage the scope no matter what you do to it.
Even like a car ignition, 50,000 volts.
The input. Well, the input first of all is protected by a 1 mega ohm resistance. Okay, and then on the other end of that resistor, they usually have clamping diodes. So even if you apply 5,000 volts to the input, there would be very little current going actually into the input channel, and then they would get clamped anyway, so the input circuitry wouldn't even see it. What you would see on the display, though, is your display would be up off the screen, okay? And if it is off the screen and you're wondering, hey, where's my display? There is actually a button here that you can press to bring your to show you it's not working on this scope. That's busted on this scope. But if on working scopes, if you press that, it'll shrink your screen down so you can see where your sweep actually is, and then you can turn your vertical knob on that. Now each channel does have a this is called Y position because it's vertical. So this is your position that determines where your channel is. Channel 2 has one too. Now I can display both channels on the scope at the same time just by hitting alternate or chop, and then I now have 2 channels there. So channel 1 is getting a signal from the function generator, and channel 2, if I turn on this microphone, I can display something here on channel 2 for you too. Hello. Yeah, there we go. So, so now I have a microphone hooked up. I have the sensitivity of channel 2 set for a few millivolts there, and so you can actually see my voice on channel 2 of the scope there.
Okay, that's cool.
And, okay, just real quick, channel 1 and 2 can also be integrated. First, let me talk about displaying 2 signals on the screen. I'm not going to do that because most of you, if you use a scope, you're probably just going to use one channel. So there are definitely reasons for using 2 channels, and if I have a little more time at the end, I'll go into that. But suffice it to say that You can add the two channels together if you want to see what channel 1 and channel 2 look like if they're summed together. If you want to see what a voice looks like if it's summed, you can hit the add button, and then you want to speak into that, and then you can actually modulate the triangle wave with the microphone. And you're just simply adding the voltage of the microphone to the voltage of the function generator. Okay? And this is really good if you're, let's say, you want to compare two. You can invert channel 2 so you can subtract the two channels too. So if you, let's say, want to compare the quality of two microphones, right? You can plug both microphones into the scope, invert one and add them, and if you speak into both microphones, it should be a straight line if the microphones are identical because they're subtracting the audio from each other. But if one has a bass response, you might see a large waveform, things like that. There are many, many, many things you can do by adding and subtracting the channels together. Which again, those are really advanced things you can do with the scope. I want to move on to a very, very, very important part of the oscilloscope called the trigger section. And if any of you have fooled around with a scope, you may have been able to get the voltage and get the sweep to work and everything like that. But all you see is a bunch of you can't stabilize the signal or really look at it to measure it. And that is what the trigger section does. Without trigger, this is what the waveform looks like. Okay? And the reason for that is because the horizontal channel is simply sweeping with a mind of its own. It doesn't care what's coming in on the input. And the input, if you've got a periodic signal like the sine wave here, its frequency will be repeating at a different rate. They're asynchronous, okay? So you're just going to get this swirling signal. This sweep is going to start at a different point on the waveform. Each time it comes around, it'll immediately start, and it might start at a different part on the sine wave. So it's just going to be a blur, okay? So the very, very, very first oscilloscopes didn't have triggers. What they did was they had a variable frequency knob, and mine doesn't work. I wish it did, but here's another way to do it, is if I varied the frequency on the generator, I can kind of get the two signals to run at the same frequency. So here the horizontal sweep and the function generator are actually sweeping at the same frequency, so it kind of looks like it's in sync, and the old scopes used to work this way. But someone got smart really fast, and they said, whoa, we got to come up with something better. And hence comes the trigger. With the trigger, you can lock right in. And what this does is, now what the trigger does is, after the scope does a sweep, it comes back, and it will wait until the signal crosses what's known as the trigger threshold. Okay, that sounded kind of complicated. Let me see if I can simplify it. You've got the reference right now. I've got the reference set at the center line. The trigger level is an imaginary line that can be moved anywhere along the screen. Okay? If the knob is set in the center, the level will be kind of in the center. If it's set positive, it'll be a little higher than the center. Negative, it'll be a little lower. Okay. If I turn the trigger knob a little to the right from center, I'll be moving what's called the threshold level, the trigger level, okay, to let's say 1 division. My reference point might be here, but I might set my trigger level to the 1st division above it just by turning the level knob just a little to the right, to the positive side. Okay? Now, here's what happens. If there's no signal, okay, I've got this triggered right now, and I can tell by where the waveform's starting that I've got my trigger set right here. If I remove the input and I set this to normal, okay, the scope has done a sweep and it came back to the start, and now it's just waiting for a new trigger, but there's no signal. The voltage is at 0, but the trigger level is like at 1 volt or so, 1 division. But if I apply a signal, then suddenly the signal comes back. And the reason for that is because, okay, let's say the waveform starts at 0, triggers at, let's say, 1 volt. The waveform starts to climb, but the scope's just sitting there, okay, it's waiting. As soon as the input's voltage rises so that it meets the trigger level, then bingo, that's permission, the gate opens on the horizontal sweep, and the horizontal sweep takes off like a racehorse, okay, and you get a trace, okay. Now I can show you a single sweep just by setting the display to single sweep, okay. What single sweep does is the scope is waiting. Well, it's not even what's called armed yet. If I press this button once, it'll arm the scope to wait for a trigger, and then when it sees the signal, it'll do its thing, and then it'll stop, and it'll wait for me to press the button again. So you can see one-shot events just by doing that.
Can you hold it? Or, like, if you hold it, does it show it for a period of time?
No, you have to actually press it.
You have to press it.
And
okay.
yeah, and that's good for seeing one-shot events. So what is happening here, the reason you're getting a stable display is because if it's set at 1 volt, the scope is waiting until the voltage of that sine wave hits 1 volt, and then it starts its sweep. And then it resets, and then it waits again, and some arbitrary voltage will come along. As soon as the sine wave hits 1 volt again, it triggers again, and lo and behold, it's exactly following the same path every single time, because it's always starting at the same place, the same phase, so to speak, 20 or 30 degrees into the sine wave. So it always triggers at the same.
You want to show that on the 475?
I'm sorry, what was that again?
Sine wave trigger. You want to show the sine wave trigger on the 475?
Yeah.
In action.
Yeah, right here. So, as you can see, I have the trigger here set for a little bit positive, about the first division above the reference point. And so you see that the scope isn't going to let that horizontal sweep do its thing until the voltage reaches 1 division, or 1 volt. Now, alternately, if I go to center, that the trigger level I now have set at the center grid line, and so the sine wave is starting right at the center of its sweep, and I can go below and see and start from a negative voltage, okay, like minus 1 volt. Okay, there's another switch right on the knob, and it's called the slope, and the slope allows the trigger to trigger either when the voltage goes in a positive direction through the threshold or goes in a negative direction across the threshold. So with the scope, with the trigger level set at minus, you can see that the sweep isn't starting until the sine wave goes from a positive to a negative direction through the threshold. So you can either have it trigger when it goes up but not down, or you can have it trigger when it goes down but not up. And there's actually a mode in the scope where it'll trigger in either direction, but that will give you a waveform that'll have a double envelope. Okay, any questions on that?
No.
Good. Now, the trigger is something you're always going to play with. Whenever you're looking at events, especially. Who wants to grab that microphone?
All right.
All right. If I wanted to, let's say, so I want you to go like, ha,
right into
Ha.
right into the mic. And I'm going to go to channel 2 here. Now I'm going to set my trigger to channel 2. Okay, that's another thing too. There's so many details, you know. The trigger can be set to trigger on either a signal coming in on channel 1, and you can do that by setting this picture. It doesn't say. I don't believe there is a switch here in this picture. But in any case, on this scope, in the trigger section, there is a trigger source switch or button, and it'll say trigger on channel 1 or trigger on channel 2. You can also trigger on line, where the trigger will actually go out and read the AC voltage off the line. That's good if you're troubleshooting TV sets which operate off of line frequency. You can also do an external trigger, where you can take an additional probe and probe something in the real world that may start a sequence of events. Let's say you know that a pulse going into a circuit will trigger a series of events, and you want to watch that series of events. You can probe that voltage that's going to start the sequence, run it into your external trigger, and then when that pulse comes into the trigger, it'll trigger your sweep, and then your sequence of events can be seen. So, what we're going to do here is we're going to see what ha looks like.
Ah. Oh, I didn't do anything.
Now, I'm going to put this on channel 2. So I'm setting my source for channel 2. You can go ahead and speak.
Okay, I'll speak. Oh, nope, that's gone now.
Keep speaking.
I'm still speaking.
All right.
Hello. Checking, testing. 1, 2, 3. Oh, there we go. Oh, and it's gone again. Oh, no, it's back. Oh, no, it's gone. Oh, it's back.
Okay. Right there's good. Okay, now what I'm doing here is, if you go like ha,
Ha.
louder.
Ha.
All right, I'm going to try that again. Try it again.
Ha.
Oh, I have that online.
Oh.
Apologies. All right, try that.
Ah.
There we go. Okay.
It's like lightning.
Yeah. Say hi again. Not too loud.
Hello. Okay.
Just go ha ha ha. Good. Okay.
Beep.
All right. Now I'm free running this right now. I have the trigger set to auto, as opposed to normal, where it waits for a trigger. Auto will wait for a trigger for a little bit of time, but then sweep anyway. Okay. That's just so you can always see a display, even if you have no voltage. So if you would just speak into that.
Okay. Speaking into it. Yeah.
Notice that
It's just doing stuff.
the softer passages are lower in amplitude, but if you go ha,
Ha. Ha.
then you'll see that the amplitude increases. Okay.
Yeah.
Let's say you just wanted to see what that ha looks like, and you wanted to capture just the ha and not the noise. Okay. What you can do is put this on normal, so that you don't have a display, and without speaking at all, if I move this trigger, okay, I'm triggering like the trigger is set right at the baseline. I'm going to turn it to the right a little bit. Now go ha.
Ha.
Okay, again.
Ha.
I'm turning down the sweep to a lower speed.
Ha.
Okay.
Well, that's cool. Whoa, that was cool.
Again.
Hey. That's awesome.
Okay, now I have the trigger set a couple
Making random
of
noises.
divisions above the ground. If there's just a small amount of signal coming into the microphone, there might be a signal there, but it won't be yet reached the threshold. It won't see the threshold, so you won't see a trace. Okay, but when this gentleman said, "What's your name again?"
Sam.
Sam. Okay, so when Sam says "ha," right then the voltage will spike up. It'll cross the threshold, which I have set up a couple divisions, so you'll be able to see the ha and the rest of the waveform, and then it'll just end. Okay, so because of persistence of vision, you can see what ha looks like without it getting too noisy, without it repeating and seeing a bunch of jumbled.
That was cool.
I'm just trying to
Speak into that.
like.
That's the microphone right there.
Oh, sorry. Trying to see if it changes, like how high or low. Like if you hit a lower note with your voice, if it. Anyway.
Sure, we'll sing. Yeah. Go like
It's not showing.
Not tricky.
Oh, you should probably like set the threshold hold lower. Or something like that.
Oh, there it is.
Yeah. So that's a note right there. You're actually looking at a note, and I can trigger on that.
Oh, it's a very nice wave. Good job, Jordan. Go to choir.
I'm in choir.
You're in choir?
Yeah.
Okay, good. We should have an oscilloscope and like hook up the oscilloscope to the choir microphone. That would be awesome.
Yeah.
Okay, so if you sing a low note and then sing a higher note, or sweep up your go
Okay.
Cool.
Yeah.
Okay, so
I'm not in choir.
So the thing about the trigger, as you can see, is that when Sam isn't speaking into the microphone, it's not triggering, and he has to get some amount of voltage before the scope will start to trigger. And this is how you can kind of get like a vocal waveform to be somewhat stable rather than just going randomly across the screen. Okay, any questions?
With a digital scope, can it pause? Can it like record and save it and keep a waveform showing from one trigger? Like record the trigger?
Right. This is a good time to move over to the digital oscilloscope. So I'm going to do that, and I'm going to request that Sam come over here with me with the microphone.
Oh, okay. I'm the resident singer?
Yes.
Okay.
And that would be...
I don't sing.
Okay, so you can... Let me take that. I'll just carry. I'll carry this.
Let's just hook it on the microphone. Okay. Oh, I need to take that.
Okay. Sam, then you can just sit over here. Okay.
Ken, the question was that is that an analog scope? You switch to a digital now. Ken?
Yeah.
The question was, is that an analog scope and now you're switching to a digital?
Oh, yeah. This is a... maybe I should just really quickly now talk a little about, because a lot of scopes these days, some scopes that maybe some of you might be buying will be digital scopes. They're getting very competitively priced. They can do a lot of cool things. Analog scopes, the way they work is they're very... I really love analog scopes because they are very intimate with the circuitry. Whatever you see in the circuit is exactly what's displayed on the screen. The voltage comes in and it goes through to a couple of plates above and below the CRT screen, and it charges the plates in varying amounts, and that makes the electron beam go up and down. And then there's plates on the side which the horizontal sweep uses too. So what comes in goes right to the screen. It's immediate. What you see on the screen is exactly what's happening in real time. Digital scopes work philosophically the same way. They've got the same, they've got your 2 input channels, they've got your horizontal sweep, they've got your trigger section, they've got your displays capability. And here on this scope on the LaCroix over here, you've got your 2 input channels here, channel 1, channel 2. You've got your horizontal sweep here, and integrated into this is also your trigger. And then you've got your screen displays down on the bottom. Also with digital scopes, you've got some additional functions like you can save. Your question was, can you save a snapshot of a sound? Right. Okay, now because an analog scope, what comes in goes right to the screen, and then it's gone. Okay, so you have to depend on persistence of vision. If you want to see what hot looks like on the scope, you'll see the waveform, and then it'll be gone. And you kind of got to look at it, and so it's not real good for analyzing one-shot events. There are analog scopes that are called storage scopes, but those have gone by the wayside, and there's no need to go into that. Okay, now a digital scope operates differently. And because of that, there are some disadvantages to it, but there are definitely some advantages to it. The way digital scope works is you've got a memory buffer, which is arranged in a circle. It's a very high speed RAM, okay? And it's basically what's called a dual port RAM, which means you can write to any address and simultaneously read out of any other address, okay?
Is that a first
And
in, first out?
that's called a dual port RAM.
Is that a first in, first out kind of memory?
Let's see. No, it's completely random access on both ends. Okay, so now the RAM in digital scopes is very fast, and so there's not much of it because it's very expensive to make it so fast. The reason it has to be fast is because you've got a high-speed input signal coming in. You may have a 1 megahertz, a million cycles per second signal coming into the scope, and what happens in a digital scope is the signal comes into your BNC just like on an analog scope, but from there it goes to your input trim, your volts per division setting, and then on the other end of that it goes into an analog to digital converter, a very, very fast analog to digital converter. It's usually only 8 bits wide, and some newer scopes are 12 bits, but most scopes are 8 bits wide. And that converter just, as fast as you set the sweep, it will just record the analog voltage into RAM. Okay, just record it right in a circle, and it'll just keep recording it. Okay, overwriting when it gets to the end of the RAM, just keeps writing in a circle over and over, and it will write into that RAM just as fast as the horizontal sweep tells it to. Okay, and so that captures your waveform. Now, on the display end, most modern digital oscilloscopes have slow LCD displays, and there's no way in the world you can display a real-time high-frequency signal on an LCD display. So instead, on the other side, on the display side of the digital oscilloscope, you've got a slower circuit that reads the data out of the RAM much more slowly, a speed that's appropriate for the LCD display. So it'll just go around, and each time it goes around once, it'll display your waveform on the screen. And it does it slowly, and it doesn't have to do it quickly because the whole waveform's there. It's already been captured by the high-speed RAM. Okay. So
doesn't that assume they're exactly the same waveform,
yes,
and that it may be capturing 20 in RAM, in fast RAM, but it's only displaying one of those 20 on the screen? It's not averaging, is what I'm trying to get.
right. The entire circle represents, if you were to take that circle and just stretch it out into a line, then that circle represents, for simplicity I'll say this, isn't exactly true, but for simplicity I'll say this, that from beginning of the RAM to the end of the RAM represents the x-axis of the LCD display. Okay? So the first address will draw a pixel all the way on the left of the screen, the next address will draw a pixel next to it, and the last address will draw a pixel all the way on the right. Now the reason I said that's not entirely true is because actually the buffer is longer than the display. So really the display might be looking at address 300 to 400 out of a 1000 address RAM. And the reason for that is because then you can, after you take the snapshot of your input signal, like, ha, right? You can examine any part of that waveform just by moving the window that you're looking at in the RAM. So now the disadvantage to digital scopes is that it takes time to fill up the RAM buffer. I mean, it fills up fast enough, but because it's so long, it may be a while before you see anything on the screen. So there's a delay. And then, slower scopes it just takes a while to process the information and get it onto the display. So you may say, ha, and then there may be a few microseconds delay before it's actually displayed on the screen. That's not really real time. Not a big deal, but you will notice that when you play with an analog scope, when you probe circuits, you can jump around. You can just see the waveform all day long, just as it is in real time, which is really great. I love doing that because I love working quickly. And so you can just probe, oh, this isn't working. It must be because of this. Nope, that's not working. You can just go all over, and you don't have to worry about things. With a digital scope, you kind of have to put the probe on, and then you'll see the display, and then you put the probe on, and then you'll kind of see the display. And also, there are some just funky things. You can just kind of tell that it's not real, But I'm probably exaggerating a little bit, just because I'm so passionate about analog scopes.
Is there any difference in terms of what it's capturing between analog and digital, in terms of the exactness, if I could use that word?
That's a great
from
question.
one to the other?
Right. There is a difference. With an analog scope, you're seeing exactly the voltage that's coming in because it's analog. Okay, there's no conversion. Okay, so no matter what you do to the probe, you'll see a little bit of something on the screen, and that's because there's a little bit of something going on at the end of the probe. In a digital scope, with an 8-bit digital scope, that gives you 256 pixels vertically. Okay, and so that means if your signal being displayed is smaller than a bit, then what you'll see is a tiny little square wave on the screen, because it's dithering between
Pixelated.
0 and 1.
Pixelated.
Pixelated. So that's the limit. But it's not a big deal, because if you're looking at a small signal, you're not going to be looking at it with so little magnification. You're going to go to your vertical sensitivity and turn it to the left to increase your sensitivity from 10 millivolts to 5 millivolts per division, maybe 1 millivolt per division. And that'll amplify the signal before it gets to the A to D converter. Okay? So you'll get the full screen resolution. So whereas if you shrink it down, your waveform a sine wave might look like a staircase. Okay? But when you blow it up, it'll look smoother, because you're now, rather than maybe having 16 bits of resolution, you've got 256 bits of resolution. Okay. So you do want to crank it up so that your waveform covers the entire screen, or, so it looks good to you, because it's really, you're just looking at it. So if it looks good to you, that's good.
Do any of these, I don't know, in terms of, can you print anything off it?
Yes. All digital scopes these days will print out for you.
But analog?
There are definitely some of the newer, this picture that I handed out to you, this is one of the later analog, Tektronix doesn't do analog scopes anymore. This is one of the last analog scopes they did, and it does come with what's called GPIB, which is a general purpose interface protocol.
So you've got to plug something into it. It's not built into the...
Right. In the old days, there used to be plotters.
Right.
Before printers, and you could plug a GPIB plotter into an analog scope. And
those were big pieces of equipment.
Yeah. But certainly, digital scopes are so much easier at plotting. If you want to plot out waveforms, then you want to do it with a digital scope. And the reason for that is because the signal has already been digitized into a data stream. And so it just sends it out a USB port to an application or a computer program that'll convert it.
Probably got its own driver to write, not a printer, right?
Right. Yeah. It's just and then to get the printout, you just go through the driver that comes with whatever application. If you buy a printer,
right.
Well, most scopes with USB, most modern scopes with USB, they have CDs that come with them. You plug into your computer, and that CD has a driver that knows how to convert a scope signal into
a printer, something
the printer can understand.
Cool.
HP printer protocol or whatever.
Do most people hook up a printer or with a digital scope or
it really depends on the field you're working in. I never do.
No.
I never do. I could see for medical reasons, if you're doing a cardiogram, you would want to print out of that or something like that. Okay, Sam?
Can you, it's like a really random question, but can you switch the x-axis and the y-axis so it's like coming down the screen?
You can't, but you can do this thing where you can using the external input on the horizontal channel, you can go into a mode called XY mode, where the horizontal channel will disconnect from the oscillator and connect directly to the external input, and will modulate the sweep according to that X input. And the vertical channel will still modulate the sweep on the vertical axis. So what you can get is Lassarier. Tom, help me out here. I forget, but it's when you want to compare phase relationships between, let's say, two sine waves. It'll draw like, I know you've seen it on Outer Limits, where there's just a symbol in the center of the screen. That's actually putting a sine wave on the horizontal channel and a sine wave on the vertical channel of two different, slightly different frequencies, almost the same. And you can make that thing squiggle into really cool shapes.
Okay.
But you can't reverse them, no.
Okay. And then,
Yeah, just the two waves.
yeah, I've got like. Okay. Can you make it do like a negative sweep where it sweeps
No.
across this way? Okay. And then one more. Is this the same kind of like family as like a seismograph? Where the needle.
Yeah. Actually, it is. A seismograph is a mechanical oscilloscope, where when the paper flows through, that's your time, okay? And when the seismograph needle wiggles, that's simply your input voltage going to an amplifier and activating two electromagnets that make a mechanical needle go, and that's your vertical axis right there. That's your input channel.
Good
So,
analogy.
Yeah.
Good point.
Yeah, good question.
What's it recording right now?
Okay, so we're going to have you say ha. And Dave, can we have the lights so I can see the controls on this? Okay, so what I need to do here is, first of all, I selected channel 1. By pressing the channel 1 button, I can display 2 channels on this, just like any other scope. I will do my second trace, and you can all see that there. So I've got my vertical knob and the second channel, but I'll turn that off for now, since I won't really be needing it. And we'll be looking at channel 1. Now I have this frozen right now. What I'm going to do is go to the trigger section, one of the very critical sections of the scope. And normally, now this is auto. This is the same thing as auto on an analog scope, where after it starts sweeping, it starts over, waits a little bit for a trigger signal, and if it doesn't see one, we'll just go ahead. And so in this way, it's just erasing what it's written. Okay. So in auto mode, it's basically recording on a continuous basis. So it's overwriting everything, just like on an analog scope. And then the readout scout is going around and reading it on the display. Now, if I go into normal mode, the display will disappear. Notice that delay. See, a linear scope, an analog scope won't do that. If I go into normal mode, it will actually freeze the display for a second and then disappear. Okay, now that I'm in normal mode, first yeah, there you go. Okay, so Sam just triggered that, and it'll go away. And every time you speak, now if you say ha,
Ha! I didn't really do much.
and you probably don't have to go ha too loud.
Yeah, sorry.
Try that. See if it triggers on that.
Ha!
All right, let's try and catch it on the positive edge here.
Ha! 1, 2, 3. Ha!
Okay, just keep saying ha.
Ha! 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 Ha!
Okay, I'm going to increase the vertical sensitivity on this so that it covers more of the vertical screen.
Ha! Ha!
I'll move the trigger to
Oh, cool.
okay, try that.
Ha! 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 Ha!
Cool.
Ha!
Be interesting.
Okay, now if you go high, it'll just freeze it.
Ha!
And I'm going to just change the time per division. Try that.
Ha! Oh, it's like one line.
Yeah, I still have the level set too close to the baseline. I'm going to increase, turn it toward the positive direction to move my trigger level a little higher. So see the beginning of the waveform. There we go. That's a good one. Stay on that. We're going to go with, instead of normal, I'm going to go to single sweep. Go ahead.
Ha!
Okay, now that's good. Now it just stored it. Single sweep will sweep once until you reset it again. On digital scope, it'll just save it. Okay, so we've got a nice signal here. Sam, do that one more time so I can get a better reading.
Ha!
And let's change the vertical again to 20 millivolts. Try 50. Try this one. We're not. Hold on a second. Try a few soft highs.
Ha, 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 ha. That's one of the few.
Try that.
Ha.
Oh, nice.
Okay. I'm trying to get the whole waveform in there. Let's try that. Let's stop with that. Oh, I got to put it on single. Try again.
Ha.
All right. Well, we'll work with this.
Sorry.
Now you can play with that.
I still think I can get a better waveform.
Need one of these, man.
You can get one to play with online, you know,
Yeah.
with your sound card.
Try it again. Try it again.
Ha.
All right, that's a good one. That's a good one. Okay, so this is the whole thing. I have the time per division set to 20 milliseconds per division. Okay. And now I can do something cool here with the digital scope. If I want to get in and look at this, there's where I can do, I can expand on A, and if I press that function, then what it'll do is it gives me a second horizontal sweep, a time magnifier, and by turning that to the right to higher and higher speeds, it will sweep across just one section of the display.
It'll like amplify it?
Amplifies the time.
Or sorry, like make it bigger. Stretch it out.
Yes.
Yes.
So first, you would go with the just the bright spot there. Down on the bottom is the actual display after it's expanded, and by getting the this one out of the way, I'll move this up a little bit and bring the bottom one down, so you can actually see the individual waveforms, and I can expand that as much as I want. I can see the really, really high frequencies here. So the expanded sweep is, the whole sweep is 20 milliseconds per division, 20 thousandths of a second. And the intensified one is 1 millisecond. Okay, so that's a thousandth of a second right there. So that on the bottom, that bright spot is expanded out. So this bottom sweep is actually displaying 1 millisecond, 1,000th of a second of the speech. Okay, and I can just move the display anywhere around here, and then I can check out various parts of the wavefront. So that's what a ha looks like. Ha. And notice that ha's actually start off. They're not really a burst like you might think, but they start increasing in amplitude. That's the hiss you're hearing right there.
Or just go ah. Would it be like
You're probably to do that. You try that if you want.
okay. That was like guttural. Okay. Ah.
Okay, there's an ah. And
No, something. This is not.
Also,
I need to work on this.
yeah,
I need to work on my ah.
say ba.
and
Ba's a lot harder.
Oh yeah.
Can you
even
see
that,
Another interesting short one is a snap,
Yeah, it
which
ramps
is
up.
just a very quick
Oh yeah. I
short
was going
waveform
short.
of snap.
yeah, finger snap.
Can you just write your good talk?
We can do a finger snap. All right, hold on a second to listen. Okay. There you go. There's a
That's
finger
neat.
snap.
Oh, there we go. Yeah, that's one big.
Yeah, when you zoom in on it, you can see the bubble.
Whoa. Wait.
So so the whole signal. All right, and you can see that interestingly,
That's
so a snap here this is very interesting. So what you see here is right at the beginning of the snap.
Is that like
This
my
is-
fingers
Yeah.
sliding?
That's your finger sliding.
Oh, that's so cool.
Yeah, it's your fingers sliding, and then when you release it, the snap is actually a high frequency burst. It's a high frequency sine wave.
Huh.
So it's like a very high frequency sine wave, but much
If
higher.
you
Probably
like
10
slow down a
kilohertz.
snap, you just like hear a slide and then like a.
How many milliseconds across
no.
that whole
You know,
thing?
if you want to see what the frequency of that is, I can just expand that out, and we can actually measure the frequency. Now, I will introduce here another cool feature of digital oscilloscopes. Oscilloscopes have this too, but I can turn on a measurement marker. I can turn on time or voltage, and with that, you've got two arrows now on the display. One's the reference arrow, and then the other
What like
is,
goes along there?
so I can, by putting the starting arrow and the ending arrow to span a single cycle, from rising edge to rising edge, a single cycle of the waveform, I can measure the frequency, and the frequency is 3.086 kilohertz.
Which knobs do you use?
Otherwise known as 324 microseconds. Okay, with the markers, that would be reference your cursor positions, reference and difference. Okay, there are also markers that allow you to measure voltage, and then these things just so you can measure the amplitude, so you can see that the amplitude of that peak there is
It's a lot of negative.
80.6. Oh, I'm sorry, it's up here. It's 80.6 millivolts for that spike, and the sliding of the fingers is only 20 millivolts. So the snap is 5 or so times higher in amplitude than the sliding of the fingers just before the
Ken, I'm
Yes.
wondering about maybe 5 minutes we could break into some hands-on activities because we've got several scopes and people can
Yeah, absolutely. Probably.
may have some more features you want to add to the.
No, actually, that pretty much does it. Unless there's any more questions.
Well, let's get some questions.
Can you data log that? Could you pull that data out into a file and look at it in another way? That will.
Yes, yes. This has because it's such an old scope. This is 30 years old. It's way before USB. It's got what's called GPIB, which was an HP invented protocol, where it's designed for scientific instruments.
General
That's-
purpose
that's-
interface bus, wasn't
Yeah, general purpose interface protocol, is it? Or
it? Bus?
bus, GPIB, right? Bus, exactly. I was thinking P. No, it's B. GPIB, and that's exactly right. And modern scopes, probably your scope, if I'm not mistaken, has a USB port in the output. This scope probably has some built-in higher level routines that will stream the data out as a file of horizontal data points, voltage over time.
What, I have a question. What's the maximum, resolution, if you will? What's the maximum polling rate that thing will measure?
Right, that's known as the bandwidth of the scope. Okay, and this scope here has a 350 megahertz bandwidth, which means that if you put a 350 megahertz sine wave into it, then the amplitude will be reduced by 3 dB. That's the roll-off point. Okay, so that means that you will accurately see a 200 megahertz waveform, for example. Anything above that will start shrinking in amplitude to zero. It rolls off. This scope here is 125 megahertz. So even though it's a digital scope, that gives you an idea of the speed of the RAM. Okay, the RAM actually fills up at a rate of 1,000 pixels at 10 nanoseconds per division. 100 nanoseconds, it will write about 1,000 locations in 100 nanoseconds. So it's very, very fast. This scope will easily display 100 megahertz signals and record them at that rate.
What's the screen dump button?
which in 100 megahertz would be 1 microsecond is 1 megahertz. So 100 nanoseconds is 10 megahertz. So 10 nanoseconds is 10 nanoseconds.
You want to say a word about this one? You kind of familiar with this model?
I played with it a long time ago. It's similar in functionality. This guy here, another digital scope. This is one of Tektronix's earlier digital scope. Again, got your display. You've got your 2 input channels. Here's your volts per division on this. Your vertical position. Channel 2, volts per division, and vertical position. And again, you've got your modes. You've got channel 1, channel 2. You can add, using other buttons, you can add the 2 channels together. That's pretty common in scopes. And then you've got your horizontal position, which just centers your whole screen usually, so you don't mess with this. You just set it there and it stays there. And then you've got your time per division. And then your trigger, again, your trigger level. You've got your coupling and so on. I didn't cover coupling. I don't have time for that. Yeah, everybody, why don't you come on up and I'll put the function generator back up.
Can I make a couple of quick announcements that I forgot to? A week from tonight, we start the Basic Electronics 101 class. We've got a couple of people signed up. Marion signed up. Kurt signed up.